Let's dive into ACID compliance. ACID compliance is a phrase that you will see often and a concept that you'll have to employ often to evaluate and decide between databases. ACID is a key set of properties, it's an acronym, that guarantee reliable processing in database management systems. Let's break down what each of these letters stands for. A is for atomicity. Atomicity ensures that every transaction is all or nothing. This means that every transaction must be completed entirely or not at all. So if one part of a transaction fails, the entire transaction fails and the database remains unchanged, which avoids partial updates that could leave the system in an inconsistent state. C is for consistency. Consistency ensures that data integrity is preserved. Every transaction moves the database from one valid state to another. This property guarantees that any data written follows all defined rules, such as constraints, triggers, and cascades, maintaining data integrity throughout the process. I is for isolation. Isolation means that transactions do not interfere with each other. And so even when multiple transactions are running concurrently, each behaves as if it's the only one. This ensures that concurrent transactions don't interfere with each other and that the end result is the same as if the transactions had been executed sequentially. D is for durability. Durability guarantees that data is permanent. So once a transaction is committed, it will remain in the system, even in the event of a crash or a failure. This ensures that committed data is stored reliably. So in summary, ACID is a standard that ensures that transactions are processed reliably and consistently. When you see the acronym, that's what that means. Now that we understand compliance, ACID compliance in general, let's take a closer look at consistency itself, which is probably the most important of the criteria. And data consistency has basically two approaches: strong consistency and eventual consistency. In general, consistency refers to all users seeing the same correct version of the data. It is evaluated based on two criteria: timeliness, so whether the data is up to date, and order, whether the order of the data updates is preserved. So with these in mind, let's look at these two types of consistency models, strong and eventual. Starting with strong consistency, in this model, every query is guaranteed to return the most recent data update. So this is achieved by requiring that all parallel processes make changes in the same order. But the strict synchronization as a trade-off can slow down query responses because the system has to ensure that all data is up to date before returning that data. So strong consistency, you can imagine, is critical in scenarios where accuracy and reliability can't be compromised, that it's of the utmost importance, such as in financial transactions. On the other hand, eventual consistency takes a different approach. Here, the system prioritizes faster query responses by allowing data updates to be temporarily out of sync or out of order. This means that you can get quicker responses from your queries, but there's a trade-off. The data might not reflect the very latest updates in the database immediately. So over time, all data updates will propagate and the data will eventually converge to a consistent end state, but not necessarily right away, as in strong consistency. So this approach works well when the speed of querying is prioritized over knowing that your data is immediately accurate, such as in a large-scale data collection effort like a nationwide census. Now, in terms of ACID compliance, you should remember that ACID refers to strong consistency. It entails strong consistency. This ensures data accuracy and reliability at the cost of potentially slower response times from the database. And then eventual consistency which is not ACID compliant, focuses on faster access to data but allows for a shorter period of inconsistent or outdated information until the system fully synchronizes. I shouldn't say shorter, just generally a short period of inconsistent or outdated information until the system fully synchronizes. So that's kind of the difference between them. By understanding them, you can kind of see how different applications might prioritize either immediate accuracy with strong consistency or faster response times with eventual consistency depending on their need. And you may be asked on the exam to decide between databases based on this need. ACID compliance ensures that databases remain reliable and consistent, especially in industries that require high levels of integrity. Let's look at some examples where ACID compliance is particularly important, and they are also examples that could show up on the professional data engineer exam, actually. Finance is one of them. ACID compliance is critical here to ensure that transactions such as transfers and payments are completed accurately, but not all data in finance requires ACID compliance. It's primarily transactional data like bank transfers or trade orders where consistency and reliability are vital, so just keep that in mind. Healthcare is another example. ACID compliance here ensures the integrity of sensitive patient data such as medical records and treatment histories. This guarantees that every update, such as a prescription or diagnosis, is processed correctly. And so it's specific to certain types of data, particularly anything that involves patient records or billing again. And then e-commerce. In the e-commerce space, ACID properties are used to make sure that transactions like order processing or payment confirmations are reliable and consistent. So if a customer places an order and the system needs to ensure that the payment is processed successfully and the order is updated accordingly, ACID makes sure of that. So that's why it matters in that context too. There are other industries where ACID compliance is important. For instance, government data, especially legal records or tax filings, they require a high level of consistency and reliability. So these industries and use cases are examples of where ACID plays a role. They could show up on the exam, but this is more than that. This is just to kind of give you an idea of how it applies and matters in the real world. Now let's talk about which GCP services are ACID compliant and how it might show up on the exam. Some questions on the exam may ask about ACID compliance. Here's a quick overview. Spanner is a fully managed, globally distributed relational database. It is ACID compliant, which is really amazing for large scale, high availability, and strongly consistent workloads, especially global workloads. Cloud SQL, it supports traditional SQL transactional databases, Postgres, MySQL, SQL Server, all of which are fully ACID compliant. Firestore offers ACID compliance at the document level, making it good for NoSQL applications that need transactional integrity. Notice how BigQuery is not on this list. That's because it is designed for large-scale analytics, not transactional processing, and is not fully ACID compliant. We'll go over these in more detail with each service, but keep these differences in mind for exam scenarios that ask about ACID requirements. And that's the end of this section on ACID compliance.